much the organizer to invite me to this workshop. So today, so it is 5 or 6 years that I'm trying to work in the connection between machine learning and physics. And today I want to talk to you about some trials that I did during these years and try to raise some questions. First of all, you can see this. This is automatically generated by the by the Acrobat. This is really funny because you use machine learning to understand what is in the picture. Okay. So first of all, I have to say that the last time I did a contribution to a conference on physics where all the people involved were physicists, it was some time ago. In 2013, I think, where we were presenting with Luigi the idea of using Lattice symbols to integrate quantum field theory and approach the sign problem there. Okay, so it's almost 8 years that I don't speak to an audience of physicists, so I hope that I'm still able to do it. What I'm doing now is focusing on machine learning in data science, and I'm in a team that work on application of machine learning for predictive models in different sectors, which go from industry to agriculture to physics. In physics, we are collaborating with people in the University of Trento, the physics department, and the TIFPA, local INFN section. And so we have a lot of things running in this field. For example, so I just want to sketch up some of the results we have. So with a PhD student, Andrea Di Luca, we are looking at inside the data of Atlas experiments, trying to look at flavor tagging problems and an automatic feature selection procedure. With other people in the XS Lima-Do experiment, we worked for automatic machine learning based method for track reconstruction inside the experiment. Then we were studying also forecast of geomagnetic storms using machine learning and time series analysis. Another different topic is using machine learning for proton computed tomography. Okay, but today I don't want to talk about all these results. I want to focus on where I found problems using machine learning in trying to understand something in physics. Okay, so you will have, I think, a lot of good results in the next talks, but in mine will be only things that doesn't work for me. Okay. Let me start with this, I think, beautiful equation. So, as you know, this is can be the QCD partition function. And when I was working as a full physicist, I was looking at this equation, which I think that summarizes very well our comprehension of the physical world in terms of theoretical physics. So we have field theory. We have almost everything under control. We know what all this symbol means. We know how we can try to solve these equations. We have a lot of techniques to solve it. We know how to compute observables with all the mathematics under control, and we can compare these observables with the experimental data. Okay. So this is what we have in physics, but now I want to go with what we have in machine learning, and let me take some minutes just to talk about machine learning, what it is. Okay, so I'm the first speaker, so I can do it. Okay, lucky me. Okay, so machine learning, what it is in a formal way, so to say. Okay. So machine learning starts with a domain set. So you have some X, some space where you have points that are objects or whatever you want, which are characterized by some features. Okay. And then you have a label attached to this. Label means that it can be a single discrete number or a continuous variables that have something to say about this X domain. And you think that there is a correct function that map your X into the Y domain. but this is unknown. Okay, so you in general in machine learning you don't know the mapping between x and y. And then there is the h. So you want to know something about it. You want to try to reconstruct this f to map this x into a h. And this is your predictor. So you want to go from x to y with another function because the f is unknown. And you want to learn this h with some specific algorithm. So let me say, okay, h in our machine learning approach is an algorithm. And then you have the learner, which is another algorithm that works on h. Okay, so what is the target goal? You want that if you take some x from your domain set, h of x, you don't want it to be different from f of x. Okay, so you want to minimize some error function in terms of h, which means that you want this equal. Okay, and obviously you need to define this L, and also this is arbitrary. Okay, so to see if your hypothesis about of h is good or not, you need to extract some points from your domain set. But the point is that you don't know the probability distribution of the x's. Okay, and then you want to compute f of x, but you don't know also f of x. So you have two unknowns. Okay, you have that you have to face off when you want to compute your h and determine your h. So what you really have is just a few or maybe a lot of training data extracted from x. Okay, usually if you think to images or something like this, it's really you really don't know anything about the distribution. In our case, we start from some known equation maybe that generate our samples. So in some sense we have the f, but when you talk about machine learning, we don't have this f, and so you have only really this data. And the only thing you can do is try to minimize an empirical risk. So loss function based on the few observations that you have. Okay, and this is quite limiting. Okay, because you don't really know b and f. And so you have a lot of problems, I would say. Okay, to be sure that what you are constructing, your h, is meaningful in the system. Okay, so just to recap the problem, we have our h of x, that is the predictor that we want to build, and we want it to be equivalent to f of x on possibly on the whole domain set of the input data. But we have only a finite number of samples that we can use to fix our h of x, and we don't know the initial distribution. So how do we choose h of x, and how can we sure that this will work on the full domain set? Okay, here is machine learning. Okay, so how we fix this h of x is machine learning. It means that we have algorithm that contains parameters that need to be fixed, and we have learner, which means we have other algorithms that fix these parameters. So usually you can have millions of parameters in your algorithm. And we sometimes we don't like that the standard model are something like 20 parameters. Okay, here we are on a different scale. Okay, but assume that you have a very good algorithm, which is your h of x, a very good algorithm to fix the parameters. Then you have fixed on the sample data your algorithm. What do you do about, what do you know about this on the general domain set? It's really hard to understand, and so you have lots of problems that can come out from here, which is overfitting, bias, and reproducibility. Let me just spend 1 minute about these slides. Maybe lots of you knows this study from started from Nature, which is the reproducibility crisis. Okay, so which means that you have done an experiment or a simulation, or whatever you want, or you have results from your machine learning algorithm, and then you want to replicate, or someone else want to replicate this, and it is not able to do it. We can think that this does not affect the research in hard science or in physics or whatever. This is not true, because 5 years ago people did this survey and found that half of the interviews from physics was telling that they have problems with reproducibility. And I have to admit that it happened also to me. So 2 years ago, one guy asked me about one result that I had with other people 10 years before, and I wasn't able to find all the code to check my results again. So it's really a problem. Okay. So come back here, we have all this thing, and we are just moving around to see if this can help in physics. So we have this plenty of algorithms, plenty of way to minimize this and to find the values of the parameters, and then we still don't know if we are doing something that will work for sure. So you can understand that I'm really happy when I have to look at this and work with this very well-defined stuff. Okay, so after this introduction, let me move to what I tried to do and I failed. Okay, Ising model. Probably all of you knows about the Ising model. The spin simple model. You have we are focusing here on 2D Ising model, where you have the spin up and spin down on a lattice defined by this Hamiltonian, the interaction, and we know that there is a phase transition around 2.269. The magnetization is the parameter of the transition, and you can compute susceptibility and so study this phase transition. Okay. Okay. Attached to this, we have scaling law and critical exponent that characterize the universality class of the transition. Okay. Compute this critical exponent is not trivial at all, and there are different methods to do that, but it's still an open problem to have this critical exponent in general for all other theory. In the Ising model, maybe we have very good ways to do it, but in other theories, difficult. So what we try to do is to use Monte Carlo renormalization group, but using machine learning to fix the renormalization group transformation. So the Monte Carlo renormalization group method is old, is from 79, 15 days after my birth. And so they introduced this exactly with the Ising model, and so the idea here is that when you apply a renormalization group transformation, you have a new system. So you generate configurations using Monte Carlo, standard Monte Carlo, on a large lattice. Then you apply a renormalization group transformation, and you have a small system which now have a different, so to say, Hamiltonian, which is given by this formula. So here you have the renormalization group transformation and H. Oh, I have to use this, I think. Okay. But the good news is that, okay, you know how to compute critical exponents from when you know the renormalization group transformation that map one Hamiltonian to the one later. And you have equation that can give you the transformations in terms of observables. So you can do that analytically, and using your Monte Carlo generated configurations, compute the critical exponent. our idea was to use autoencoders to produce the renormalization group transformation, because in principle the renormalization group transformation are arbitrary in some sense. Okay, and we wanted that is the autoencoder to choose what is the renormalization group transformation. Okay, what is an autoencoder? Is a deep learning network made of two parts. In the first part, okay, so here is our input, so our Ising configuration. At the beginning, the Ising configuration is made of -1 and 1, so spin down and spin up. We map this in 0 and 2, in 0 and 1, just because it's simpler for the network to learn this. And so you start from this, you apply convolutional layers, okay? I take for granted that everyone knows convolutional layers. So this convolutional layer moves on the configuration and generate another configuration which is smaller, okay? At the end of the encoder part, you have a smaller number of variables that represent an encoding of your initial configuration. After that, you go in the opposite direction. So you increase the using convolutional in the opposite direction. So you increase the size of your system until you reach the same size of the beginning. And the idea is to minimize the difference between the input and the output configuration. So you want that your network will be able to reproduce as much as possible the input. Obviously, it is almost impossible to have exactly the same configuration, because something here, okay, is for sure lost, okay. But your hope is that in this small number of variables, you have encoded as much information as you can to reproduce a similar configuration. Okay. So usually under normalization group transformation used in an Ising model is the majority rule. Okay, when you just keep for example, these 4 spins, you sum up and you generate your new spin on the reduced configuration. Okay, and so you have double the scale of the system. And so this is half of the initial dimension of the configuration. In the same way, instead of using the majority rule, we use our convolutional layers. Okay, so we have filters that act on the configuration and generate a new configuration. Okay, and this is fed in the convolutional autoencoder, and you train your autoencoder to minimize the function, and so at the end you have some filters that generate a reduced configuration. After that, what we use is the Monte Carlo renormalization group method equations to compute our critical exponents. And this is what we have. Okay, so for eta and the nu, the truth is 0.25 and 1. Okay, here on the axis is the size of the system. So we start from under 28. So the first calculation is for 64. Okay, then you go until 8. Okay, and you see that you can go quite closer to the true value. Okay, and we compare this with the majority rule. Oh. Okay, so here we are very close to 25. Here also to nu, and also better than majority rule. First of all, the first thing is that with machine learning, it's really hard to have confidence intervals and understand what is your uncertainty on the method, because there are many ways that you can define uncertainty in machine learning, because it's inside the single algorithm with different algorithm, so with different way of learning the same algorithm. So there are many ways that one can think about errors, but there is no standard definition of error apart from the statistical error. But here there is the statistical error, but is inside the size of the point. Okay, what is the point here? That we observe that there is this strange behavior, because we are just growing and then going down, and there is no real reason from our understanding that this will happen. So we tried to find some mistake in the code. Well, we didn't find it. We thought maybe it was because 128 was too small. Okay, and maybe if I go to larger and larger lattices, there will be some, I don't know, oscillating behavior here that can be explained some way. So we consider 512 lattice, but the behavior was exactly the same on the same point. So after 2 iterations, okay, we have the same strange behavior, and we don't know why. And to debug this is really difficult because you don't know if there is something physical in this or there is something in the algorithm you use. And so, in my opinion, you don't really have a clear procedure to understand this. Okay, so here is where we stopped because we weren't able to understand this problem. So for a physicist, I think it's really a problem. Okay, if it will be just recognizing cat from dog, I will say, okay, we are here, good, so I'm fine. But as a physicist, I want to know what's happening here. And so this was the first failure. Then we move to phase transitions. Okay, also here we are looking at the Ising model. Okay, but here we want to study the transition instead of looking at the critical exponents. So we know that there is this phase transition, and we have the magnetization for the as an order parameter. Once again, we can use unsupervised method to try to see if machine learning can detect this phase transition, and we use autoencoder. Once again, in this case, we tried different things. So using convolutional layers or convolutional with a with a single convolutional filter or with many filters and with different numbers of layers. In this case, at the end, we use as latent variables only one number. Okay, so the point is we start from a large configuration. In some way, we decrease using convolutional layers the number of variables until we reach a single latent variable, and then we reconstruct. And we want to understand if something in the latent variable can detect can be mapped in a comprehension of in the representation of the phase transition. What we did is train the network using configuration only at t equal to infinity, which means we use just random configuration to train the network. Okay, there is no reason why the autoencoder should be able to reproduce exactly random configurations. Okay, but something can be there. Okay, and then once the network was trained, we generate with Marco Chain Monte Carlo standard techniques configuration at different temperature, and look at the representation z of the configuration. So z is the latent variable. Okay.
Sorry, what do you train it on the infinity?
Sorry?
What do you train it on with those configurations at infinity?
The autoencoder. We train this autoencoder here. Yeah. Okay, just to reproduce random configuration. So in input you have a random configuration, and you want that at the output have the same random configuration. Okay, and here you have only one number, which is the latent variable associated with this configuration.
So nothing to do with phase transitions at all.
No, absolutely not. Okay, it's something that so your network learns something about these random configurations. Okay, you don't know what. Then I moved to configuration at different temperatures. Okay, and looked at the z produced. So now I'm not training. I just using my autoencoder in inference, and in particular, I'm only interested in the encoder part. Okay, so input configuration taken from this interval, and see what is z. And this is this is what happened. Okay, this is just an histogram of the distribution of the latent variable, the absolute value of the latent variable, and what we see is that they distribute differently for different temperature. Okay. In particular, at T equal to infinity, they are really close to here. Okay. Then they start spreading, and then there is this strange behavior here. Here is just because this peak here is just because I cut it at 15. Okay, because otherwise it would be going. And so you have this, and you have to invent something to compute your expectation value of z at a given temperature. And we try different things, which are simply the mean of the absolute value, okay, minus the mean obtained at the random on the random configuration, or just the standard STD, the standard deviation of the variables, and this is just a standard deviation with other different network, and all these quantities are on top of the magnetization. So this C can be interpreted in some way as capturing the phase transition of the model, which is, in my opinion, at the beginning was really crazy because it was only trained with random variable, with random configurations. But then, so I asked myself why this is happening, and this is why. Okay, so I generate configuration with fixed ratios of up and down spins. So all up, 80% up, 50%, and so on, which means, so because I'm using only 0 and 1, which means that you have, I don't know, half of them are 1 or 80% are 1, and so on. And then I look at the Z, okay? And look at this plot here. What happens is exactly that the ratio is perfectly the relation between the z, the latent variable, and the number of spin up is the relation is linear. Okay, which means that my network is just learning to count the ones. Okay, but this is good in some sense because if you look, so the count the number of ones in a configuration which is given from 0 and 1, it's exactly the definition of magnetization when you have -1 and 1. Okay, so in this specific case, the only thing that the network learns is exactly the magnetization, but it's just a coincidence because in this specific for this specific physical system, it's like this. So it was by chance, so to say. And to check this, we moved to a different model, okay, which is the XY model. Okay, here the thing is a little bit more complicated because you don't have only spin up and spin down, but you have continuous variables. Okay, the form of the Hamiltonian is the same more or less, but you have a continuous variable, so you have angles. And so you have this form of your Hamiltonian, and we know that also here there is a transition, which is a topological phase transition connected with the presence of vortices. And also here we have our magnetization, which represents our order parameter for this transition. Okay, so we try to do the same as before for this different system. And so here we use a lattice size of 128. We use the same idea of autoencoder trained on t equal to infinity. Okay, but come on, here it's really different because you have something much more complicated because you have angles, and so there is lots of difference between the Ising model and this one. And then, as before, we generated our Monte Carlo samples and look at the Z. Okay, these are the distribution of the Z. And there you see that also in this case, the distribution changes with the temperature. And, oops, if we use the same as before, we use the standard deviation on the Z as way of extracting the observable, we find that also in this case we are perfectly on top of the magnetization. Okay, here is done with different kind of networks with different number of filters per each layer. Okay, but for lots of different combination, we have the same result. Here, the plot is normalized in the way that you have the same number at the critical temperature. Okay, because otherwise it is not normalized in the same way. But also in this case, we have no idea. So while in the Ising model, we were able to find a way to map what the network learns with what is the with the order parameter of the transition, with what is our understanding of the order parameter. Here we have no idea on how to map this. So here, once again, we failed to understand.
I'm sorry, Feng Yu is asking, I mean, whether this is sensitive to the autoencoder loss function.
Okay, this is a good question for the XY model. Okay, yep. Because in particular, I didn't talk about that. So usually for the Ising, for example, we just use as a loss function the mean square error. Okay, so just the difference between the two. In this case, we also use the energy. Okay, we introduce. Okay, so we have, first of all, you cannot use the mean square error because you have angle and periodicity on the angle, so you need to use a different mean square error that takes care of the periodicity. Okay, but then we also added another loss function, which is we want that at the beginning, at the end, I don't know, the energy should be the same. Okay, I have to admit that I looked now at these numbers that was generated in 2017. So I'm not sure if I tried with and without the energy constraint and what is the difference. Okay, I should redo the calculation. But there's
a question by Barak. Maybe you can keep that in charge.
Sorry.
Well, Barak, can I unmute and ask the question?
Yeah, Barak, I mean, you can unmute and ask the question.
No, nothing. There were no fixed symmetry. Absolutely. No, because it was generated on the random variables, on random configurations. So it's just a random configuration that your autoencoder, okay, that doesn't know anything about nothing apart that you introduce this energy constraint on the loss, which I don't know if it plays some role in this context, because it was introduced before when I was studying another thing. So I was trying to reproduce a fixed T, the same configuration. Then I so that if there is this energy and also magnetization bound, the ability of the network to reproduce exactly the same configuration was increasing. Cosa devo fare? Lasciarlo fare?
No.
No.
Actually,
okay. No, but Barbaros is well-known people. Okay.
Barak wants to say something.
Yeah, I was actually asking. I mean, the autoencoder is some nonlinear transformation, and you're choosing some order parameter which presumably needs to break a certain symmetry. In this case, U1 in a very particular way. So in the general case, how would you choose the right latent variable so that it will break your symmetry, the symmetry involved with the phase translation, in the way you want to? I mean, suppose you want to generalize this to other symmetry groups. I mean, you need to choose. Usually, the order parameter is designed to break the symmetry in a particular way. and here I didn't follow how you choose the order parameter.
No, here, sorry, here I didn't choose nothing. Okay, so what I did was, okay, I have configurations extracted from, so one thing is how I train the network, and another thing is how I use it for inference. So when I train the network, I just use a random configuration generated with a no, it's not it's just random. So I throw one number between 0 and 2 pi for each lattice size. Okay, then I have these layers of convolutional networks that ends with one single number, which is the latent variable. So at the end of this procedure, I have only one number that I don't care what it is. Okay, then I use this latent variable to generate, again, using inverse convolutional layers, another thing which is interpreted as a configuration for the XY model. Okay, and I want that this input will be equal to this. What I minimize is the difference between the angles here and here. Okay, for each of the lattice size, and the energy of this computed on this and this configuration. I don't know if the energy plays some role in this analysis. I don't think so at the level of the training. So there is no constraint at all on what happens in this latent variable. Okay, it's a pure autoencoder. It's not variational autoencoder, so you don't have any loss attached to this latent variable, but only the only loss is, can you mute yourself? Sorry. Is only between the initial and final configurations. I hope it is clear now. So yeah, I don't tell. So the only thing that, so the arbitrariness here is how I sum up all the how I use these latent variables to define an expectation value of something. Okay, and I just use, for example, the standard deviation of this distribution at given t. Okay, this is arbitrary. Okay, and I don't know if I have something to do with the symmetry of the system. Okay, maybe, I don't know. Okay, but the point is that if I choose between the mean or the standard deviation, I have the same. Sorry, this was the Ising, but it's the same. Okay, so
Big fan, you have another question.
Yeah, thank
sorry, I mean, if you want to continue, I guess we can also continue. I mean, it's up to you if you want to take the question or not. No.
yeah.
Sure. Okay. It's more like a comment. So I see you. Let's go back to if we go back to the like a Ising model or model, this like up and down case. We started with like 128 square bits, right? And then you say you encoded it into something like 32 bits. Then the loss function is more like, well, if you use something like a L2 norm, it's scale invariant, right? So what really happens if you try to minimize that loss on an even uniform set of training samples, what wouldn't it be just saying, well, for each of these, I'll cluster my input according to some scale and then map it to a representative sample, just based on my 32 bit. The 32 bits I have, right? I'll start from just evenly divide the input space and map it to those samples. And because you're using this L2, which doesn't really care about the scale or something like that, then well, it would be picking this fairly. That's why you see it's a fair sort of representation, and that's all. That can also explain why different temperatures you still get this sort of a different kind of location. It feels like that. So it's more. It feels like this, or in other words, it feels like this last function you pick has this sort of like symmetry or energy or whatever. It's there. It's not like the encoder is transparent. You throw your assumption into the encoder already by picking the last function. That's just a comment like that. I'm not sure if this is really right, but it feels like that.
So I agree that the form of the loss function for sure is influencing the full training procedure. Absolutely, and because the L1 function is transparent from so is as you said. Okay, so the symmetries are inside there. It is fine. So I'm sure, but still. I don't understand why it works. Okay, at least for the XY model. Okay, so I can imagine that. So I don't understand why the Z representation should be significant in terms of the. So it should be exactly equivalent to compute the magnetization for the XY model. I think maybe there is also an analytical solution of this problem. I didn't find it.
Yeah, well, thanks for the comment. Yeah, thanks.
Okay, so I have to say that this is more or less everything I have to say. I just want to leave with a small provocation. Okay, so we will see, I think, the next days a lot of way of using machine learning to approach physical problems. I am really curious if there are ways to rewrite physics, okay, to rewrite the comprehension of the physical world in terms of machine learning. Because we have hundreds of we have centuries of history based on mathematics and starting from velocity, acceleration, Lagrangians, Newtonian, whatever, that help us to understand this physics. But is the unique way? Is the way the world is written? I don't know. Okay, so it's really puzzling me if there is a different way of write this and understand. So this ability to predict something will imply our comprehension of the phenomena. Okay, so this is a more philosophical question maybe, but there are ways to start with thinking about this. For example, I was trying to see, okay, look at the gravitational law. So gravitational law describes a lot of systems, but in principle, we can start from the very beginning, which means that we have collected data about where objects are in space. Okay, and look at we are able to predict the next position of this of these points. It is possible to do that with a machine learning algorithm that can generalize well. Okay, which is not just to predict the next point, but predict the full orbit and or the full trajectory and then orbit of the planets when you have a different velocity. So what we need to do that in a general way that we are sure that the machine is learning something general instead of just predicting with a good accuracy, which is not understanding the problem. Okay, the next point. This I think is interesting to think about it. Maybe on spare time. Okay, but okay, I have this question and I left it for you. Okay, thank you very much.
Thanks a lot, Marco. So if anyone has a question, please go ahead. You can either raise your hand, I mean, online, or just take the initiative.
Yeah, could I maybe just ask in response to the provocation? So it's an interesting thought to use machine learning to maybe gain some more deep insights. But of course, as you said, machine learning, it's very hard to place error bars on your output, systematic errors. And sometimes it'll just do something that is not physically accurate. So how do we do you have proposals, I guess, for how to distinguish these cases or really gain control of the machine learning?
No proposal at all. So I have to admit that I think that this will be the far end of our world of our journey on machine learning for physics. So but it's also connected with what we have on machine learning in general frameworks. So exactly, for example, compute observables. What does it mean? So it is what we intend now. So it's just really a provocation. Okay, so I don't have any answer on that. Okay, what I did in the last couple of weeks just to play with it was just trying to see if at least the machine learning can predict the next point when you have two particles interacting with gravitational forces without giving them the mass, for example, because also the concept of mass is a concept that we introduced to understand what's happening. Okay, so the machine learning needs the mass to be able to predict something, or when it learns, there are some sort of mass inside the weights. We don't know how to search for it, for example, without imposing ourselves a form of the network that in some way have as input the mass. So I think that it's an interesting but absolutely open problem.
Okay, thank you.
Hello, in the next talk. So I wanted to ask regarding the XY model, which showed that you use energy as loss function along with the MSE. So, but in the MSE, how did you take care of the periodicity of the angles? Like
Then I wrote instead of the MSC. Okay, you have an angle version that you just introduce a modulus of the angle, and when you have on the opposite side, you counted the right distance. Okay, when you okay.
So once the process phi you have.
Yeah, but I found that loss. I didn't invent it by myself. Though it's known in literature.
Another question I have regarding the Ising. So you showed that you use the CNN, right?
Yeah.
And you could have used different layers, different number of layers. Do you think that impacted the critical exponents that you get, or is it constant?
Okay, for the renormalization group transformation case, okay, you need to mimic what happens in a renormalization group. Okay, so you need to fix the size of your kernel of the convolutional network. Okay. Yeah. And slide on the network on the same in the same way as you do. Okay, with the normal transformation, and then so you finished with a half of the dimension of the initial because I choose b equal to 2. Okay.
Yeah, yeah.
And then it stops. Okay. So
Okay.
you want that you want to go from something which is your full network and half of the size. Okay.
You go from suppose dash dot dash by 2 and
exactly.
So, on,
so how you do that? If you can do this with different number of convolutional layers, I think so. But with 2 times 2, you should at some point enlarge again and then go back.
Because
can be
you
done.
showed a very nice plot, which is this correlation between if you choose 8% positive and then 10%, and this 1-to-1, right?
Yeah, but that was on the other problem, not the renormalization group problem, but on the phase transition problem. Okay,
yes.
which
So,
is different. On that side, you can use whatever you want because you want to finish it with only one latent variable. Okay.
Essentially, that would mean that if I give any configuration which has just the same number of spins as the training set has, right? It
Yeah.
will still give me the same plot of the M, right? That you obtained from the set, like the sum.
Yeah, it means that it just counted the number of ones you have in that configuration. So your latent variable is just that number.
Any cluster sitting formed or anything.
No.
Doesn't matter where the locations are. It's
absolutely.
For the number.
For this way of approaching the problem, yes, it's just
so that could, so if you take the critical temperature that you extract from the phase transition that you obtain from the Z, and then you try to construct the finite size scaling.
Yeah, sorry.
Of the critical temperature.
Okay. But
and then you can also get the critical exponents out of that as well, right? So you won't see the physics, right?
I didn't try that for the with the same autoencoder because you cannot use the same because the same that autoencoder ends with one single variable.
I'm just saying that you use that Z, that magnetization that you obtain from the Z. You extract critical temperature out of it,
Ah, yeah, okay, yeah.
and then you do transfer scaling.
Yeah.
And then
You can do this. Yeah, yeah,
So
sure.
you
I
won't
didn't
see
try.
the same scaling as the physics scaling, right?
Sure. Yeah, yeah, that should be the case. I don't know.
And this is what I wanted to know, that whether this scaling will change depending upon the network that you choose to work with in the first place.
Okay, so for the renormalization group case, we try with different
Not
networks.
the RG network, I mean the phase transition.
Okay, but should be the
I
same.
see. Okay.
I
Thank you.
think we are.
Well, very quick question by.
Okay, okay.
I have one that's very quick. All of my questions. Okay.
The time is wrong there.
The time.
Okay.
time is wrong.
I was thinking. It's late, but not so late. Sorry.
Okay, thanks, Marco. So just, okay, this question will be very quick. You trained at the autoencoder on Monte Carlo sample produced at t equals infinity, right?
Yeah.
So if you had an Ising model with an anti-ferromagnetic coupling, so the samples would look similar at infinite temperature, but you could not see the phase transition with what your autoencoder doing in this case, right? Because if you sum up the spins, you
Yeah.
can also get 0 in the ordered phase.
Yeah.
Right?
I think so. Yeah.
Yeah.
Should be.
Okay, thank you.
Good. Thank you. Oh, there are also questions.
I don't know.
No, I haven't seen one. I mean, I guess there are no questions, I mean, from online participants. Oh, sorry. So, yeah, no questions from online participants. So I think, well, we should thank Marco again. Thank you. And,